to make sure I get a shot of that shirt. Okay, good.
See how I did one more. Yeah, but I did better than half a lot of my mind.
Hey, did you get the email though? Yeah, that whole extra there. Did you get that? Did you get the email? No.
Oh, no, is it an email? I mean, I saw it as your email, but I just haven't had a chance to gander at it yet.
Take a gander.
I haven't got mine. I was in here.
What's your full name?
Phil.
Huh?
Cass. Phil Cass. Right there. Cass. K-A-S-S.
Oh.
It's a blue book, so I mean.
Oh.
I think it is. Yeah. Ew.
That's on the bottom. Oh, shawl. That's on the bottom of the pile.
If you email me, I'll send you a link to these videos.
They're on the.
You're on YouTube?
Yeah.
I started watching them, but I was
You
like,
watch them?
What?
His videos.
Oh, my.
Don't tell them.
Which video?
No, those.
that was, what do you?
Oh, these videos. Well, at the end, maybe. No, I didn't. Do I look nice?
Yeah. Just like you do now.
Okay.
Camera takes away 10 pounds in
Yeah.
about 20 years.
Yeah.
About 20 years. So in other words, you look 20.
I mean,
To take away 10 pounds, I have to start running, and I'm too lazy. And then I usually.
Well, you're running your mouth up there an awful lot. That was for sure.
Okay. So, number 8. We're considering some subset of rational numbers, as far as I can see, right? So set D is all rational numbers with additional provision
Oh.
that P does not divide N, and P is a prime number, is a prime. Okay, so that's our subset of rationals. Clearly, it's a subset of rational numbers, right? Just some additional condition. For example, if I take the simplest prime 2, what does it mean? It's all fractions which can be presented with odd denominators. That's about it. Of course, fraction which can be presented with odd denominator also can be presented with even denominator. But if a fraction is presentable like this, I will put it in my bank of rationals. So what is the question? That it is an integral domain. Now, integral is obvious. Why? It's subset of rational numbers. And rational numbers are a field. Anyway, field, not field, we know perfectly well. If product of two rational numbers is 0, one of them should be equal to 0. So just by virtue of being subset, it should be integral. Domain is a different matter. Why? It's not clear why it is. What is other component of domain? Or maybe first component. It's a ring, right? It should be a ring.
So close your range.
So it should be closed under addition and under multiplication.
And invertible.
No.
No, that's
No,
that's
invertible is for field.
That's
For ring, it just, and if we check closure, that's it, because it is a subset of a field, which is also a ring, right? Subset of a ring. In order to check that it's subring, we just have to check closure. And because of definition on our book, we also have to check that 1 is there.
Yes.
Well, 1 is certainly there, no matter what is P, because 1 is 1 divided by 1.
yeah.
And 1 is not divisible by any prime. So 1 is there. So what I have to check? That it is closed under addition and multiplication. The fact that it is closed under multiplication is kind of easier to check, because actually multiplying fractions is easier operation than adding L, sort of. Why? Because if I multiply two fractions, denominators are multiplied. If I have two fractions such that their denominators are not divisible by P, then product of these denominators is also not divisible by p. This we know. That's where it's essential that p is prime. If p won't be prime, that's not true, right? Because of that, it is closed under multiplication. In order to check that it's closed under addition, you have to perform your operation, but again, you know, when you add two fractions, you can take the product of denominators as common denominator, and then everything will be expressible, right? A divided by b plus c divided by d. I always can take bd as denominator, and again, b is not divisible by p, d is not divisible by p. Therefore, this product, and here we'll have then ad plus bc. So it is closed under multiplication and addition, therefore it's a subring. We check that one is there. And the fact that it is integral domain comes for free because it's subset of a field of rational numbers. Okay. With this part we dispense. What else? They want us to find out what is the field of fractions of this object. And they say it's all rational numbers. Why is that? Well, one is there, but also any integer is there. Any integer n, positive or negative, I present it as n divided by 1, and I see immediately it's in our set. Since all integers are there, and in field of fractions I must have ratios of all elements. I have ratios of any two integers. That's it. Actually, what is interesting, it's clear from definition of what we're discussing, since it's a subset of rational numbers, that the field of fractions is a subfield of field of rational numbers. Right? It sits inside of rational numbers, so all ratios are also sit inside of rational numbers. And you know what? There are no subfields, proper subfields of field of rational numbers. Any subfield of field of rational numbers is all rational numbers. Why is that? Suppose you have a subfield of field of rational numbers. 0, of course, is there, right? 1 is there. So 1 plus 1, which is 2, is also there, right? And 3 is there. And 4 is there. So any integer is there. Because it's a subfield, it's closed under addition. Since it's also closed under subtraction, all negative numbers are there, integers. But if I have in my subfield all integers, then their ratios will cover all field of rational numbers. Okay. Unlike field of real numbers, which has a lot of subfields, and some of them we researched with you. You remember we looked at elements which look like this, where A and B are rational numbers, and we showed that this is a subfield. In fact, there is a lot of subfields in field of real. If you think about real numbers as vector space over rationals, it's highly infinite dimensional vector space. Now that's interesting because this allows you to play some interesting things. Okay, do we have other questions today? Other questions? Do we have other questions? No? Yes? No? Go ahead.
Yeah. Page
No? Rise and shine.
page 260, number 12.
260, number 12. Is it also homework?
Yeah.
Recall that an element of a commutative ring is said to be nilpotent. I don't know whether we recall it or just use what is written further as definition. If some power of this element is 0. So it's called nilpotent. What we discussed with you, similar term, idempotent. You remember? Idempotent when squared give you the same, right? And this is nilpotent. Okay. Show that set of all nilpotent elements of a commutative ring forms an ideal. Show that has non-nilpotent elements. Show that any prime ideal contains. Okay.
My only question is just part A. I think that I basically have the right solution, but
Okay, but
I
you want
just-
to double check.
yeah.
So we have a ring, right? And then we have this subset M. And what we're interested in, whether it is ideal, right? So remind me, what is the definition of ideal?
It is closed under addition
Closed under
for any
addition.
two things that
Okay,
are in
so
there.
A and
Something
B is an N. We want somehow to deduce that A plus B is an N. And another one?
For A and M and R, R times A is in M, so it absorbs the multiplication.
Okay, which one is easier to prove?
I have the second one.
Second one is very easy, right? Because this means that for some k, A in power k is 0, and then RA in power k is R in power k, A in power k is also 0. Okay, now, we are using here big time that the ring is commutative, right? Because if ring is not commutative, this formula is wrong. You understand?
Oh.
So commutativity is very important. Clearly, right? Because otherwise it will arrive k times and you don't have ability to solve. Okay, so that's more interesting, right? Well, let's put what is our data. What is our data? We know that
Those don't have to
there
be
exists an N and M, so that A in power N and B in power N are zeros, right? Correct? What we have to deduce? Somehow we want to deduce that A plus B in some power is also 0. Yes?
I think in the book it says like A plus or minus B is element N.
Yeah, okay. You will see that there is no difference.
Okay. That was my biggest question, was why minus?
Oh, where is it in the book? Why plus or minus? In definition of the ideal.
Yeah.
See, you don't need it because it is closed under multiplication.
Right.
And of course, if you have 1 in your ring, you also have negative 1 in your ring, right? And B multiplied by negative 1 is negative B. So
Right.
if A is in the ideal, then B is in the ideal, that minus B is also in the ideal.
Yeah.
And closure under addition then tells you A plus B must be in the ideal, and A minus B must be in the ideal, and A plus RB for any R must be in the ideal,
Okay.
right? So I don't know. No, so
Great, that's good.
basically you have to check that some question mark will work. I mean, not this question mark, but this question mark. Let me put some pen. Okay. So, how can I handle this? Again, I have to use that my ring is commutative, because otherwise it's all just not correct. But I know how to raise A plus B in power n. I know that it is A in power n plus n times A in power n minus 1 B plus and so on. There are some coefficients there, I don't care. So general term is something like this. Some coefficient, and I don't really care what it is. A n minus I, B I, and all the way up to B in power n. So how we can ensure that this sum is 0? Well, I don't know any better than to ensure somehow that every summand is 0. If I know that every summand of this sum is 0, then of course I understand the sum is 0, right? And so from this I see, for example, if I take n to be large, then certainly A in power big N and B in power big N will be 0, right? Because just enough for me to take this big N larger than both numbers. But how I can ensure that this term is 0? Well, here I have the following idea. If either n minus I is larger than or equal to n, or I is larger than or equal to m, then this guy is indeed 0. Right? Well, if this is larger than n, then a in this power is 0, right? If a in power little n is 0, then a in any larger power is 0. And the same story for b if I is not. Okay. So if I add these two things, right, then it looks like that if n is larger than or equal than n plus n, I will be in business.
And you already took n to be that big.
It's up to me, right? You see, there is no restriction. So what I have to show that this sum insufficiently large power is 0. It's not told to me in power not larger than blah. In any power. Okay. Well, actually, if you look at it more carefully, that will be n plus n minus 1. Why so? Look at this expression. So, how it is not 0? That's bad case scenario, right? This thing, I cannot guarantee that it is 0 if both conditions, n minus I is less than n, and I is less than n are met. If I have these both conditions satisfied, right, then I cannot guarantee that this product is 0. The same thing, right? N minus I is less than or equal than n minus 1. Right? And I is less or equal than n minus 1. So if I add these two guys, it will give me that n is less than or equal than n plus m minus 2. So if this condition is satisfied, I indeed may have a monomial which is not 0. But if it's not satisfied, in this case, it's not satisfied. So if I just take it equal, it's not satisfied. Every monomial is 0. Okay? So in order to do it, of course, you have to have this idea to use binomial expansion, which is not so, off the wall here in this context. You want to show that a plus b in some huge power, so you're using a formula. No big deal. Make sense? Okay, actually, probably next one is more interesting. Was B easier to show? Yeah.
I thought A was the easiest one.
Okay. And how about the last one? Last one is, if you look at it correctly, it's obvious that it belongs to any prime ideal, right? Because if a in power n is 0, then a in power n belongs to this prime ideal. 0 belongs. But a in power n is a multiplied a in power n minus 1. So one of the multiples is there, one of the factors. If a is there, we're done. If not, then a in power n minus 1 is there, which again you can split as a multiplied a in minus 2 and so on. Proceed until you hit 8. Yeah. This thing even has special name. It's called nil radical. And the radicals in general play an important role. But when you are dealing with non-commutative settings, then it becomes much more involved, and there are still some open problems which are not completely solved about things like this. But it's not my field, so I really don't follow carefully what is proved, what is not. But there is some very famous conjectures called Curti conjecture, which is still open. Okay. Any other questions? Do we have other questions? Other questions? No other questions? Okay.
From that table, you should get like repeating terms in some of the columns, right?
What are you talking about?
For problem 4.
For the first column, for column 4, you had.
I do.
Okay, tell me on which page, then it will be easier for me to look at it.
259. 259, number 4.
259, number 4. Let me look at 259, number 4. Give a multiplication table for such a ring. Okay, now, we're factoring out polynomial x squared minus 1, right?
Yeah.
Is it reducible or irreducible? It is reducible. So result is not a field. Okay? So you have repetitious elements. Say you have zeros, you have 0 divisors. For example, x minus 1 multiply x plus 1, in this arithmetic is 0. So you should have repeated elements. Only those elements which are relatively prime to this one, their units and corresponding rows don't have repetitions entries, but otherwise, okay. In any case, no, it's Z3, right, okay, great. Any other statements, questions, declarations? Go ahead.
Z3 is a field, right?
Z3 is a field.
And Z3 is an ideal of Z.
What?
Is Z3 an ideal of Z?
No.
Because I think
You're confusing two things. Z3 is a homomorphic image of Z. You have a homomorphism from Z to Z3. What is this homomorphism? It sends all numbers divisible by 3 in 0, all numbers with remainder 1 to 1, all numbers with remainder 2 to 2. Now, Z3 certainly is not an ideal in Z because it doesn't belong to Z. You cannot find in Z elements which behave like elements in Z3. If you take, say, 0, 1, and negative 1, try it. And what is 1 plus 1? It is 2. Okay, well, you can say maybe it's negative, but 1 plus 1 plus 1 is 3, which is not 0 in Z. Okay, so this is a homomorphic image, and so that's the connection. Any Zn is a homomorphic image of Z, but none of them is a subset. Even subset, not just even subset is not. Okay. Anything else? Any other doubts? No? Okay. So tell me, what are we supposed to cover in this chapter 2?
Just permutations.
Permutations. Okay. Did we understand notion of permutations? So what is a permutation? What is a permutation?
Just a different way to.
It's just a bijection. Just a bijection. Now, we will be primarily concerned with bijections on finite sets. But in principle, you can look at bijections on infinite sets as well. So you may have the infinite situation. So there are two different ways to record a permutation. If you have just unrestricted permutations of set of, say, 3 elements, and the same would work for n elements, then one of the ways to do it is the following. Write 1, 2, 3, it's kind of our input, and below, say, output. This would be adequate recording of permutation, which means that our bijection take 1 to 2, 2 to 3, 3 to 1. Okay. So you can record exactly, you have 6 different possibilities, all 6 of them you can record. Another way is the following. Let's look at this permutation. Let's start with 1. 1 goes to 2 goes to 3 goes back to 1. So it has a cycle of size 3. It goes like this, right? 1 goes to 2, goes to 3, goes back to 1. Any permutation can be written in this form. Split in cycles. Now, it's interesting, but probably I shouldn't explain it this way, but I can. If you tell that 2 elements of your set are related, if one of them can be obtained with help of permutation by several applications of your bijection, so I will tell you that I have the set of n elements, I'll call it, say, you know what, let me just call it S. And I have some permutation, I'll call it tau. And I take element I in S and element J in S. And I tell that J is related to I if by definition j is equal to tau applied several times, maybe, I don't know. So there exists a case such that tau in power k applied to I. So if I push I k times I have, this will be actually equivalence relation. And so it will split all set on not overlapping classes. But I will prove it differently. So what I want to prove, that if I have two different cycles, they don't intersect. First of all, why I have cycles at all? Now, of course, for set of size 3, it will be easy to see, but I have a general situation. So I have a bijection from set S to set S. And for argument's sake, we will think that this is just n elements, and they're numbered 1, 2, 3, and so on. So suppose I started with 1, and I have tau, I have 1, then I have tau 1, and I have tau square of 1, right? If I apply it again, tau cube of 1, and so on. Now, and so on I can do infinitely many times, right? But I have well-defined many elements. So it's clear that there should be repetitions in this sequence. So there are some i's and j's, natural numbers, such that t in power I applied to 1 is the same as t in power j applied to 1. Is this clear? Otherwise, I somehow have to find room in finite set for infinitely many elements, right? But I submit that if this is true, and let's again, for argument's sake, assume that I is less than j, then 1 is actually equal to tau applied to 1 j minus I times. Now, where this is coming from? What was tau? Tau was a bijection. So tell me, if you have a bijection, do you have an inverse bijection?
Yeah.
For any bijection, you have an inverse function. Call it tau in power negative 1, reasonable notation, and apply it to both sides. What will happen? Instead of this equality, you will see equality tau in power I minus 1 applied to 1 is equal to tau in power j minus 1, right? If you undo 1 tau. Do you understand? Is it clear that if I have, so you remember definition of inverse, tau 1 and tau combined give you identity, right? Something which sends every element to itself. So if I have, say, tau in power negative 1 and tau cubed, you remember this is associative operation. So I can split 1 tau here, and so I have tau inverse tau, put bracket here, I have tau squared. But this is identity, and identity applied to tau squared is tau squared. So it behaves like usual exponent. And if I repeat this several times, I will get this equality. Okay? So, from fact that there is a repetition, I actually showed with you that at some point, 1 will go back to itself. Of course, I can find the smallest number for which 1 goes to itself. Right? I may have many numbers like this. If it's, say, t squared of 1 is 1, then of course t cube of 1 is 1, right? T in power 4, clearly I know. Well, t in power 1 maybe is not, but t squared and t in power 4. It's like order, right? So I can find the smallest number. So suppose d is the smallest number from n, natural number, so that tau in power d of 1 is equal to 1. I submit that then all numbers 1, tau of 1, tau square, all the way up to tau in power d minus 1 of 1, they're all different. Why is that? Of course, I have to use the fact that d is smallest. And here I have, which is 1. Well, Suppose it's not the case. Suppose I have two entries here, say t in power a of 1 is equal to t in power b of 1, where I can assume that a is less than b is less than d, right? If I'm not right and these elements are not all different, right? Then I can play the same trick, and then t in tau in power b minus 1 of 1 is also 1. But that's a contradiction. Because of this inequality, b minus a is certainly less than d. And you remember I have chosen d to be this small as possible. So no repetitions. So I have a cycle, right? Number go to different, to different, to different, to different, and then finally it goes back. So I have a cycle. Let me draw it like this. I started with 1, here is tau of 1, and so on. Here is tau in power b minus 1 of 1, and here is finally 1. Okay. So I showed that we indeed have cycles. Next, what I want to show that different cycles cannot overlap. They cannot have common elements. So suppose I have first cycle, I'll call it C1. Maybe I started with 1, for example, and wrote it. And then I took some element which is not there, because of course, if I take any element from the cycle itself, I won't go anywhere, right? Because if I take, say, this element, on the next step it will go to this one, to this one. So they will still be inside of the cycle. And then I take C2, and what I'm saying, suppose they have a common element. So there is an element S, which belongs to this cycle and to this cycle. Okay. Okay. Well, so S is there, and now I can manufacture this cycle just like I did with 1, right? This shortest cycle, which consists of different elements. So that, just I started with S, I pushed it, and the same logic as with 1, S1, what's the difference? I have this. Okay. Okay, so this is some element also of cycle C1. So I have cycle C1, and here I have my element S. So what is next element in C1?
Tau of S.
It's the same as here.
Oh.
Because it is bijection, right? It's 1-to-1. Right? If I have, or anyway, it's not even important if it's 1-to-1. But it's a function. If I have this input, when I apply tau to it, I will get the same thing. So these guys are the same. And the same, of course, is true for cycle C2. Suppose I have this cycle C2 like this. I cannot be like this, because if I start with C and I am pushing with tau, it must go to the same position. I cannot go to different position. Okay. So they coincide. Okay, anyway. Any element, so if I start with S in this cycle, if I push it, I get next element. If I push it, I get next element. And after finally many steps, I will cover all cycle. Just like we did with 1, right? But then this must be this cycle. It's not important with what I start. That's the point. If I start with this one, right, I will get exactly the same cycle. No difference whatsoever. So that's why cycles don't overlap, and that's why every permutation can be written as combination of cycles. Now, there is one thing which is tradition. Cycles of size 1 are not written. They just omitted. So if I have something like this, I will record it just as 1, 2. That just by agreement, all elements which are not recorded are just cycles going to itself. Okay. So these are two nice ways. In a sense, this cyclic recording is better than this one. You also see it requires less writing, right? You have to write less. But it also reflects some deep properties. Okay. So we have this proposition, so R is disjoint. Okay. So cycles are disjoint. Okay, there is the theorem here, it's also proved, so you can read at home and compare it with our discussion. Another observation which is made here, and let's also discuss it. Suppose you have two permutations which are just simple cycles. Just one cycle, one permutation. Say I have 1, 2, 3. It's one permutation, but say my set consists of 6 elements. And then another permutation is say 5, 6. So I have two permutations, you understand. This permutes 1 sends to 2, 2 sends to 3, 3 sends to 1. 4, 5, and 6 are just staying put. This one sends 5 to 6 and 6 to 5. But all other elements which are not written are staying put. And so there are bijections behind this.
I have a quick question about that. If we get shown something like that, we obviously can assume there's 4. because 1, 2, 3,
What?
4. If we get
Those
shown
are
something like
separate.
that, we can always assume 4 is in it, because 1, 2, 3.
Oh, 1, 2, 3, and 5, 6 is written. Yeah, so
Right.
certainly, yeah. We usually
But
just.
what about, say, for example, if 7, 8, 9 all loop back?
We, from this record, we won't be able to judge. But it will be told to you. You have a set of Bly elements. So you have a. So claim is that this bijection actually commute. That if I just write product of these guys just as a succession. It seems to be pretty obvious, yeah, because they don't overlap. And what one does with 5 and 6 is not affected, but what another one does with 1, 2, and 3. But of course, if they overlap, then situation is different. So help me to compute. I have a set now of 3 elements, and I want you to help me to compute product of these two guys. What is this product? So how you should attack this product? Think about it. Where the element 1 will go? I always can start with element 1.
2,
So where 1 will go?
2.
Why to 2? I understand 3. I apply this one, right? We send 1 to 3, right?
We 1 through 2.
Wait. So 1 sent to 3 by this one. What this does to 3?
Stays put.
So it doesn't go anywhere.
Why'd you do the one on the right first?
So 1 goes to 3. I can start with any element which I want. What's the difference? I like to start with 1. You want to start with some different element.
Well, why
I
don't
don't
you start
mind.
with one on the left side? 1 goes to 2, 2 stays put.
How compositional functions work?
Gotcha.
First this one applied, then second one applied.
Gotcha. Usually we have some like nice brackets or something, but okay.
Well, but that's you.
Or like a
well,
little-
you're big enough to understand it without brackets.
Well, now I am.
F in front of each.
Okay, so where 3 goes? Tell me where 3 goes.
3 goes to 1 and 1 goes to 2.
So, the upshot, 3 goes to?
2.
To 2.
Okay.
Okay, where 2 goes?
1.
Done. So composition of these two cycles give us this 3 cycle. Basically, it's not important, this fact. What is important that from this example, I want you to understand how to compute this composition. Right? That's how you're computing it. Okay? Make sense? You may have more here, 10 cycles written, but that's how you will do it. You can always start with 1. It doesn't matter. Now, what will happen if you didn't exhaust all of it? In this case, we exhaust all of it. But if not, then you take any element which doesn't belong to this triple and look what, say, for example, our set is actually of 4 elements. Well, what will happen with element 4? Nothing. It will stay put. This doesn't rework any element 4 in a different position. This also keep it so. You understand?
Can we do another one?
Sure.
Bigger?
Certainly.
So I can make sure I.
Like a
Give me an
10
example.
on this side and like
1, 2,
a 15 on that
3.
side.
Okay.
Yeah.
1, 2, 3, 3, 4, 1. How about this one?
That's cool.
Okay, so help me. I start with 1. Where 1 goes? Not true.
1.
It goes to 1 because this 1, yeah, I'm applying this, goes but send it to 3. But then this projection kicks in, which sends 3 to 1. Since I started with 1, that's it, just singleton. Okay, I didn't exhaust situation. What happens with 2? Let's look what happens with 2. Where 2 will go?
3?
Yeah, because this won't affect it and this 2 will send to 3. Where 3 will go?
4?
4, and nothing here. Great. Where 4 will go?
Wait. 2 went to 3.
Okay, start with 2.
4 stays at 4.
Take 2. This doesn't involve 2, so
Yeah, so
this.
you gotta go to the.
So I
first.
have to go to this. So 2 goes to 3.
Mhm.
Where 3 goes? To 4 here, and 4 stay. Okay, so I have 4 here. So where 4 goes?
One,
We
then
go
one
to
goes to 2.
1.
And then?
1 goes to 2, and we are already at 2.
That's it.
Okay.
So that's what we got. Okay. So it's as simple as this. If you want to multiply 2 permutations, that's how it works in cyclic notation. Of course, in this notation it's even more obvious, because here you just have your bijections, you understand? Here you see 1 goes to 2, then you look at the second bijection where 2. Okay, so it's not a challenge at all to compute these things. Now I don't know whether we're going to use it or not. Okay. Now, last time, okay, let's look at all propositions here. Okay. 2, 3 permutations. So it starts with definition. We understood, yeah? So it's just bijections. We have a bunch of examples. We have definition of a cycle. There is also notion of length of a cycle. What is the length of a cycle? What is the
How many
length?
different numbers?
Number of elements involved. That's it. Yeah. So these were 2 cycles. This is 3 cycles. Okay.
But their product is
No, product is combination of 1 cycle and 3 cycles. What I'm just saying. Definition of length is not all transposition, it's just for cycle. 1 bijection may be a combination of many cycles.
so we have 1, 2, and 3, which is like
For
the
example,
3.
you can think, of course, this is not because it's overlapping, so it's not 1 permutation. But say this is a permutation.
Of length 4.
No. It consists of 2 cycles.
Okay.
One of length 1, other of length 3.
Oh, okay.
Motion of length is defined for a cycle, not for permutation. Permutation may be 1 cycle, maybe many cycles.
So we have to write that 1 there?
No,
We don't, okay.
no.
that's what I thought.
I just wrote it because I started with it.
Okay. Yeah, we could.
That will be correct. But this permutation is not a 3 cycle because it has 4 elements.
Mhm.
So it is 3 cycle and 1 cycle. Permutation. If we're talking about structure. Okay. So if we have disjoint cycles, as we understood, they commute. If you have 2 bijections, which are just simple cycles, and these cycles don't overlap, then from what we these computations, it's clear that they commute. Every permutation can be written as a product of disjoint cycles. What do you mean What do they mean by product? So suppose I have a 4 permutation 4, which is written like this. It's one permutation, but of course it's also composition of permutation 3, 4 and permutation 1, 2. Right? If I compose them, that's exactly what I will get. Right? Yes?
Maybe.
Maybe. Most probably. Oh. Okay.
Yeah. Now that I think about it more.
Okay. Okay. Now, presentation, you have to understand, really. There is uniqueness of presentation, but of course, this presentation or this presentation are equivalent. Because, so, take this in consideration when we're talking about uniqueness. Uniqueness up to reordering. Right? Uniqueness up to reordering. Okay. Now, what do you call an order of permutation? What do you think? Order of permutation. Did we have a notion of order of unit? What was an order of unit?
I mean,
By itself to get 1. So let's apply the same definition to permutation. How many times you have to multiply it to get identity? If we have such a number, of course we'll take smallest such a number. We'll call it order of permutation. The claim, yeah, claim, a claim. Order always exists for permutation. For every permutation, there is the smallest number such that when you repeat it this many times, you get identity permutation. How we can prove it? Well, let's think. Suppose I took this permutation of mine and I present it as this product of disjoint cycles. Okay? Well, I have some, say, suppose I'm dealing with a set of size 10, for example. You will see again that this 10 has nothing to do with it. So I have I1, 1 cycles, I have I2, 2 cycles. You got the drift, right? I have, I don't know, I10 of 10 cycles. 10 cycles. Of course, these are some numbers, but there is a connection, right? I say I1 plus 2I2 plus 3I3 or and so on plus 10I10 must be equal to 10. Now, where this is coming from? There is I1 1 cycles, and so I have I1 elements which go to itself, right? Then I have I2 2 cycles. I have I2 pairs like this, exactly like 2, each contain 2 elements, right? This is, by the way, not very important, but nevertheless, right? They contain 2 elements, and this, you remember, they are not overlapping. So how many elements are busy in 2 cycles? 2 multiply number of 2 cycles. With 3 cycles, it's 3 multiply number of 3 cycles. So, for example, if I have 1 cycle of size 10, then all these numbers are 0. But never mind that. I have some finite number of cycles, right? Okay. In which power I have to raise cycle of size 1 to get back? To power 1. In which power I should raise cycle of size 2 to get back? Square it. How about cycle of size 3? Cube it, right? Because it sends 1 to 2 to 3. If I cube it, then 1 will go to 1, right? 2 will go. So size k cycle, I have to raise into power k.
do you want to do an example for that, or is that pretty clear for everybody?
How about this cycle? 1, 2, 3, 4. What it does? Sends 1 to 2 on first application, right? Sends 1 to 3 of the 2 applications, right? 1 to 2 and then 2 goes to 3. So if I apply it twice, 1 will go here, right? If I apply it 3 times, what will happen? First application, send it to 2, second will send it to 3, third will send it to 4, right?
Okay.
What will happen if I apply it 4 times? Goes back.
Okay.
So see, picture is like this. You have this 1, 2, 3, 4, and it rotates like this, right? 1 goes to 2, 2 goes to. So if you do 4 clicks, it will go back. Yes.
I just want to check to see if I'm understanding.
Mhm.
So if you have something like that one, that's 1, 2, 3 is one cycle, then 5 and 6 is another cycle,
Mhm.
they'd have to be at cycles of size 6 to get back to where they were.
They are not cycles of size
That's
6.
not cycle of.
But if you raise it into power 6, it will work. Because power 6 is even, and so 2 cycle will go to itself. And power 6 is divisible by 3, so 3 cycle will go to itself. Very good observation. So what will happen here? So size k cycle, I have to apply k times to go back. So if I have bunch of cycles, in which power I have to raise all this bunch together, so that every cycle will go to identity. So if I have 2 cycle and 3 cycle, what is the smallest power?
Is that 2 and 3?
Huh?
What number is it?
2 cycle and 3 cycle. What is the smallest power I have to raise?
5.
No, how 5? 5 will distort 2 and distort 3, but 6? Okay. So what is the 6? What do you think? It appears as what?
Least common multiple. Least common multiple.
As least common multiple of 2 and 3. And of course that works for any set of cycles. You take their lengths, and if you have 10 cycles of size 3, you don't care, you just take one representative, right? So you take least common multiple of different sizes of cycles which are presented, and if you raise them to this power, you will get identity. Is this clear?
So if you have
Because if you have 10 cycles of size 3, it doesn't matter. 10 or 1, you have to raise in some power, which is divisible by 3. Not 10 times divisible by 3, but just 1 time, because every 3 cycle raised into this power will go to identity, right?
It's kind of like there was an old puzzle where they would show you a racetrack and horse and say, this horse in one lap goes twice as fast. as
Yeah, something,
How long will it
yeah.
take for them all to get back to the
Yeah,
first?
exactly, something like this, yeah, something very, very similar. Okay,
Oh, let's quit horsing around here now.
so,
So,
okay,
when you say raising to a power,
okay, so suppose,
wait, when you say raising to a power, it makes me think of multiplying something by itself.
yeah, of
But in
course.
this case, it seems more
What is
like.
raising to a power of bijection?
But in this case, it seems more like another iteration of like a program or something.
It is what it is.
But it's a composition of bijection. That's what our multiplication. So in sense, it's iteration of the same
Composition of
bijection.
itself.
Yeah, composition with itself. So suppose I have a cycle. Well, suppose I have the structure like this. What is the minimal power I have to raise this to get identity back?
4.
4. 4. Because I have a 4 cycle, and I have a 2 cycle, and a 4 cycle, and what is the least common multiple of 2 and 4? 4. Now, why 2 is not enough? This, of course, will go to 1, but if you apply just square this, then what will happen? It will become 2 cycles. 2 cycles. 3 will go to 5, 5 will go to 3, 4 will go to 6, 6. But it's not identity, you have to square it
Can
again.
we run through that 4 times to get back to 1?
Oh, no, not back to 1, to make it look like it used to look. You're thinking of, imagine I had like
To have it as identity bijection.
So you will eventually get back to 3.
You have a bijection on
You pick
these
any
4
one to start
elements.
with?
Yeah, if you start
You
with
have to get
6,
back
by
to
the time you're done, you should have 6 again.
Okay, so no matter which one you pick, you run it 4 times.
And then you wind up with what you started with.
You will get 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to 6. Alright?
that kind of identity, the identity of whatever you put in.
Identity as transformation. You get identical.
And 6 goes to 3. So you get back to, so yeah, 4 things, you get back to
On
3.
first step, 6 will go to 3.
Yeah.
Count your fingers. On next step, it will go to 4.
Yeah,
On next step, it will go to 5.
Yeah.
On next step, it will go to 6. How many fingers? 4.
can we do something that involves the first one too?
Do the same
Was
thing.
this one?
It'll go to 1.
On first one will go to 4. On second one, 2 will go to 1. On third one, 1 will go to 4. On fourth one, 2 will go to 1.
Oh, okay,
We'll go-
So 1 will go to 1
oh, okay.
after 4 steps.
Huh,
1 goes to 2, 2 goes to 1, 1 goes to 2, 2 goes to 1.
so in
So,
that case,
Identity is identical bijection. Bijection which takes every element to itself.
so in that case, depending on for this example, depending on which element you take, it could be less. For 1 and 2,
yes,
it's just 2.
yes,
But you have to
exactly.
find something that
But
satisfies any element.
I want all bijection after this many iterations to become identical bijection.
Okay.
Not some parts and pieces, okay?
Alright.
So the upshot is interesting. Of course, we can prove it out of general mumbo jumbo, and I can do it also. But then I won't have this number which you told me, least common multiple. Okay? But we proved here with this constructive estimate that any bijection after raised in such and such power, depending on its structure through cycles, will become identity. Now let me give you a general mumbo jumbo proof. If I have a set of n elements, how many different bijections I have? Already talked about it. N factorial, right. Why? Number them 1 and so on up to n. 1 can go on the first, to any of the n guys. But after that, 2 can go only to n minus 1 element, because 1 is already occupied by 1, by image of 1, and so on. So that's why you have n factorial choices. Be as it may, what is important for me is that I have finitely many bijections, right? Of set of size n, I have finitely many bijections. So, if I take a bijection and the square of this bijection, it's another bijection. N cube of this bijection, it's another bijection. And so on, if I take all powers, it cannot be that they're all different, because I have finitely many bijections altogether, right? So it means that for some numbers I and j, tau in power I is the same as tau in power j. Right? Because I have bijections, identity, tau, which I can think that tau in power 0, right? Tau squared, tau cubed, and so on. I have infinitely many representatives here, right? But I have finitely many bijections altogether, so there should be repetitions. I cannot have infinitely many and finite set. Repetitions means I can find I and j such that they're of course different, and I have this equality. And again, I can assume, for argument's sake, that it is smaller, right? And then if I apply inverse bijection, just like before, I will get tau in power I minus 1 is tau in power j minus 1, right? And so on and so on. So after several steps, I will get that identity is tau in power j minus I. And if I don't know anything about bijection, I cannot do any better than that. It exists. But if I know its cyclic structure, now you know its least common multiple, which will work. Least common multiple, which will work. Okay, so any bijection. Now, this number is called order of a bijection. Order of permutation is this smallest number at which you have to raise it, how many times you have to iterate it, in order to get identical bijection. Okay? Okay. Now there are some special bijections. They have special names. They are called transpositions. Transposition is a 2-cycle. Transposition is a bijection which exchange position of 2 elements. And every other element stay put. Why transpositions are important? Because in fact, any permutation can be obtained as composition of some number of transpositions. And it is pretty clear. Say, suppose 1 goes to k. Okay, 1 goes to k. So I can take first transposition which exchange y and k, right? So 1 will be in its place. Then k will go to L. What L apply after that? I will apply transposition, will send k to L.
I was thinking for a second that had a lot to do with the game of 15, but not so much, I guess. Because with the game of 15, they're all adjacent.
Yeah, you
Space
also
they're
have
not.
some transpositions there and permutations.
So they're all adjacent.
We're
Well-
going to show in cup scanner.
Okay, so suppose I want to get 1, 2, 3. So what I will do, first I will send 1 to 2. Okay, so this will send 1 to 2, and 2 will send to 1, right? But I want 2 to go to 3, right? So I will now apply 1, 3. Right? So now this indeed will send 1 to 2, and it stays there because I don't have 2 anymore here. And 2 will go first to 1, then to 3.
Here goes back to 1.
Now if 1 goes to 2 and 2 goes to 3, then 3 must go to 1 because it doesn't have any more room to go. You remember, it's bijection. And of course we can check it. 3 go to 1. So that's how you can present any cycle if you want. Suppose, let me do one more and then you will see the common drift and you will try to understand it result. So 1 goes to 2, 2 goes to 1, but 2 goes to 3, right? So next one is 1 goes to 3. So let's look what happens. 1 goes to 2 as we want and stay put. 2 goes to 1 and then to 3, that's what we want. Now we want 3 goes to 4. Where 3 goes? To 1. Oh. How about 1, 4? It will put 3 in place and we're done because now I don't have any choice. 4 must go to 1. So every cycle can be presented in such a product. And since we have a bunch of non-overlapping cycles, that's what we will do. Okay? And so any permutation can be presented as a bunch of transpositions. Now, is this presentation unique? Of course not. You may have a lot of different ways to do it. But what is interesting, if you consider a given permutation and present it one way through transpositions or another way through transpositions, oddity of number of transpositions does not depend on presentation. If it was presented one time with help of even number of transpositions, any other permutation, any other presentation of this permutation has also even number of transpositions. It cannot be that the same transposition, same permutation one time is presented as composition of even number of transpositions, and the other time as odd number of transpositions. This will be preserved. And those permutations which are presentable with even number of transpositions are called even permutations, and those which are presentable with odd number of